In this video, I'm going to show some of the figures I plotted for the demodulation of the DSBSC's AM signals. To demodulate the signal, we need to modulate. So to modulate the signal, I generate a message signal. You can see this is low frequency. The frequency is, I plot 1 second here. How many cycles here? 1, 2, 3, 4, 5. So cosine signal with frequency 5. Okay. And now let's look at the frequency domain here. This, if we take Fourier transform of this cosine signal, we should have two specs sitting at 5 and minus 5. The magnitude should be half for those delta functions. You can see here, this is 5 and 5, the magnitude is 5. This is a frequency domain for the message. Now, after modulation, we multiply by high frequency cosine. You can see the red here. That's the message. The amplitude of the carrier is changing with the message. Okay, so if we take Fourier transform of the modulated signal, we should have these two specs move to carrier positive. The carrier frequency here is 100, move to 100 and to minus 100. So let's look at the frequency domain. Here, that's 100 and negative 100 here. What's the magnitude? The magnitude should take a half because of the modulation property. The magnitude for the carrier is 1. So I don't have any scaling factors for the carrier. Now this is a modulation. The signal's been modulated already. Now let's look at the demodulation. In the demodulation, I multiply by the modulated signal here. This is a time domain signal with the same cosine signal with the same phase. So which means that the phase been synchronized. This is what we got here after the multiplier with the same carrier before the low pass filter. Now, this frequency domain, we should say two specs, the signal sitting at 5 Hertz and two specs sitting at 2 FC. It should be 200. So let's see if we got it or not. You can see here. So this is the two specs sitting at 1 and minus 1 here. And you can see this is a 200, double of the FC. And notice that the magnitude of those delta function here, and this is a double by this one because this is a modulated signal, right? This modulated signal moved to 100 and minus 100, and there are two specs overlap at the centered at the frequency 0. So therefore, two of them plus together, you're going to have 0.25 here instead of 0.125. So now I change the phase shift pi over 2 as the demodulator. We lost the signal. Cosine pi over 2 that equals 0. The modulation part is all the same, but let's look at the demodulation. This is a time domain waveform. That's what we got. Let's look at the frequency domain. I take Fourier transform of this. You can see what I have. This frequency component sitting at 200 Hertz and minus 200 Hertz. That's double of the carrier and nothing here. And this low frequency, remember our message is our 5 Hertz, two specs here. Can go back to figure 2. This is our message. You need to have two specs at 5 and minus 5. If we don't have this, two specs in the frequency domain, we lost the signal. So this is why the phase shift of pi over 2 is not good at all for the demodulation of the DSBSC signals. And remember that in the lab, you're going to perform all of this. That's in lab 4.